So what does seawater, glacial ice, alcohols like wine, or alloys like bronze have in common? Well, they're all mixtures. And if you remember back to your early years in science, you might have started to classify different things based on what they're made of or what they're composed of. And you might have been able to talk about things as pure substances, that is, all of the particles in a particular substance would be the same, or mixtures. That is, that if we got down to the particle level, we would see that there are different particles that make up a mixture. And we can further subdivide these mixtures into homogeneous mixtures or heterogeneous mixtures. And homogeneous mixtures are ones that appear all the same, and heterogeneous mixtures are the ones that appear like they have different phases or different components. And we're going to focus right now on those homogeneous mixtures, and we refer to homogeneous mixtures quite often as solutions. Even though you might look around and you can't see air, and you would argue that air doesn't have a smell or a taste, it is composed of different things. That is, if we were to take a look at the particle level of what air was composed of, there would be a whole bunch of different gases present in it. We would have things like nitrogen gas, which is the major component of air. We would have oxygen gas. We'd have some carbon dioxide. There'd be some trace argon gases. There is a mixture of a whole bunch of different gases within the air that we breathe. And back to our not so clean air, we can detect through breathing and just looking that there is particulate matter or little particles suspended in the air. And we refer to this type of compound as a suspension. Now, the distinction between these two things is that a solution, especially within the fluid phase, and when I say fluid phase, I'm referring to solutions or liquids and gases. When they're in the fluid phase, they should be transparent. It doesn't mean they necessarily have to be colorless, but we should be able to see through them. Now, when we have something that's a suspension, what we have is particulate matter that is very, very small within a fluid phase. So in this case, we would have particulate matter, small particles that can be detected within the fluid, and we refer to this as a suspension. As I've discussed with solutions already, they're a mixture. They're made up of different components. And there are two major components that we talk about when we describe a solution. And those two major components are the solvent, which is the substance that does the dissolving, and the solute, the substance that is dissolved. And typically in a solution, we have the solvent, which is in greater quantity, and the solute, which is in lesser quantity. Although it is important to note that sometimes you can get two substances that when mixed together will mix together indefinitely, like alcohol and water, and we say that these two substances are miscible in one another. That is, M-I-S-C-I-B-L-E, miscible. Now, when we take a look at a solution, it's also important to understand that there has to be something dissolved in that solution, that is the solute. So in order to discuss dissolving, I think one of the easiest things to do is take a look at table salt, sodium chloride, which, as we know, will dissolve in water relatively easily. But let's take a look at the mechanism by which this comes about. So salt will come in contact with water, and water is a polar substance. That is, it has a slightly positive end and a slightly negative end. And as we know, with salt being an ionic compound, it's made up of positively charged cations and negatively charged anions. And what happens when something comes in contact with water is that water is going to try and pull apart this ionic compound by having the positive end of water attracted to the negative ions of the salt, and the negative ends of the water molecule attracted to the positive ions of the salt. And if the attraction of the water molecule for the ion is greater than the attractive force of the ions for one another, the water molecule will pull those ions and separate those ions from the substance. And this is a process that we refer to as dissociation. Generally, we would talk about it in terms of dissolving, but when we deal with ionic compounds, this is a term, again, we have to be familiar with when discussing solutions. We say that ionic compounds dissociate into their component ions, or the ions that make up that formula, when they come in contact with water. And just generally, we say that this is a dissolving process. On the flip side of this, if we were to take a look at a molecular compound like sugar, the water molecules too would surround the sugar molecule, with the exception that since it's not made up of ions, it surrounds and separates the entire sugar molecule rather than splitting the sugar molecule apart. And that's an important distinction to be able to make between dissociation of an ionic compound and dissolving of a molecular one. So when we discuss solutions, there's a couple of terms that we have to be familiar with when we're describing the quantity or amount of solute in a particular solution. And one of those is concentration, and the other one is solubility. And so we have to be able to distinguish between these two terms because at first glance they might appear to be the same, but there is a very important distinction that we have to make. So when we deal with these two substances, it's the maximum amount of solute, remember the thing that is dissolved, that will dissolve or dissociate in the case of an ionic compound in a given amount of solution when we're dealing with concentration and in a given amount of the solvent when we're dealing with solubility. And of course, these both have to occur at a specific temperature. So again, let's pay very close attention to that. Remember, the solution is the entire mixture, including both the solvent and the solute, whereas the solvent itself is irrespective or different than the solute. So for example, if we were talking about solubility of table salt, it would be how much table salt or sodium chloride is in pure water, whereas we were talking about concentration, it's how much table salt is in that entire mixed solution composed of both pure water and sodium chloride. Now let's just focus on concentration for the rest of this video. I'm going to take a look at solubility in a subsequent vodcast, but there's a couple of things I want to deal with when we talk about concentration. First of all, there's a qualitative aspect to it. Remember, qualitative means that we're not dealing with numbers, it's just observed properties. And that is the terms that you're probably already familiar with, and that is concentrated and dilute. And these are relative terms. What that means is when we're talking about concentrated and dilute, we're comparing two things. So something can be more concentrated than something else, but that doesn't make it the most concentrated thing on the planet. It just means relative between those two things, it's more concentrated. When we talk about concentrated, it just means that we have more solute per unit volume than something else. Now let's take a look at the quantitative relationships involved in concentration. And when I say quantitative, I'm of course referring to mathematical and numerical relationships that exist with concentration. And we have to remember that concentration itself is an intensive property. That means it doesn't matter how much or how little of the solution we have, the concentration is going to remain constant throughout. So if we were to take different volumes of the same solution, let's just say a sample of seawater, the concentration of that seawater or amount of salt in that seawater would remain the same whether I have a milliliter of it or a liter of it. Extensive properties like the volume or the mass of the water would change, but intensive properties like the concentration would not. It's important again to remember that concentration refers to the amount of something in something else. So there can be a whole bunch of different units associated with concentration. For example, we could have a mass in volume concentration, where there's grams dissolved in milliliters. We could have a volume concentration, where there's milliliters dissolved in milliliters. And if we think about metals or alloys like bronze, where one metal is dissolved in another metal, we have a mass in mass solution. And some of you may be familiar with terms like parts per million or parts per billion, and those too are representations of solutions. But the one that we're going to focus on, the one that's most used in analytical chemistry, is molar concentration. Sometimes in older texts you might hear it referred to as molarity, but we are going to deal with it in terms of molar concentration. And the units for molar concentration are moles per liter, or moles over liters, and that helps you come up with the mathematical relationship or the equation for molar concentration. That is, molar concentration, denoted by a large C, is equal to moles, N, over liters, representing volume, in V. So we have all of our units for that particular relationship, just understanding that molar concentration is moles per liter. So if you want to say that you need to memorize this equation, then yeah, I'd say you need to memorize it. It probably, after the number of moles equals mass over molar mass, is the equation that you're going to use most in introductory chemistry. In fact, it might even be the equation that you will use the most in introductory chemistry. So it is worth understanding. So hopefully after watching this video, you have a better understanding of the solutions that you come in contact with on a regular basis, what comprises or makes up those solutions and how we can classify them, as well as the relationship between the amount of solute in a solution and the amount of solvent or the amount of solution that we have in order to communicate the solubility or concentration of that particular solution. But most importantly, that you're able to understand that the amount of solute within a given volume of solution is going to allow us to communicate its concentration, and in chemistry that we use molar concentration or moles per liter to be able to communicate that. So remember, understand that equation, C equals N over V, memorize it, learn how to rearrange it to solve for number of moles, or in some cases volume, and you'll be better off when you come across concentration calculations in chemistry. Thanks for watching.